Our final section is the divergence theorem. And before we really get too deeply into the divergence theorem, we're going to find that it's actually an extension to 3 dimensions of Green's theorem, or a broader form of Green's theorem. So let's recall Green's theorem from a few sections ago. And we'd written Green's theorem in this form we see in the notes here as the line integral of f dot n. So this is the normal component of a vector field f along a curve C, and C is the positively oriented boundary of a region D, and Green's theorem told us that that line integral on the left is equal to this double integral on the right of the divergence of f. Okay, so this gave us a nice, of course we saw Green's theorem, we can evaluate the line integral if that's the easier way to go, or we can integrate the double integral on the right of the divergence of this function f if that was the easier way to go, or use the other versions of Green's theorem, specifically the tangential versions. So there is an extension of this, and this is essentially what the divergence theorem is. So recall again from Green's theorem that, looking below, we've got a sketch here. We have a surface D, or really we have a region D in the plane is a more accurate way to put that. And it's got a positively oriented boundary C. So that's our 2-dimensional version of this situation, and we'll say in R2, just to reiterate that this is a region in the plane. And the divergence theorem is really going to be an extension to a solid B with a boundary of B. So the boundary of a solid is a surface. So this is just the outer edge of some surface we'd see, and really all along this thing is a surface boundary enclosing this solid region in R3. Okay, so to emphasize that in R3 here. So just like the boundary curve of our region D in the plane has a positive orientation, we'll need to choose a positive orientation arbitrarily for such solids, and that'll be the outward pointing normal of a solid. Okay, so we'll only use this for simple solid regions. We'll make some extensions to finite unions of simple solid regions within these notes, but the proof that the book provides only proves it for simple solid regions, which are of type 1, 2, and 3. So if you go back to when we first started looking at solid regions, we can look again at what type 1, 2, and 3 solids are. Actually, this is back in triple integrals in the previous chapter. Now, for any solid region that satisfies this, we'll be able to state the divergence theorem and use it. Note that, as such, the boundary of any solid that's type 1, 2, or 3 is going to be something like a parallelepiped, or a rectangular box, or, well, in this case, not quite rectangular, an ellipsoid or a sphere, something that's not multiple pieces, and that completely encloses its contents. Okay, there's some convexity going on too, if we think about that as well. So it's not a donut, might be one thought, or a torus. Okay, so let's see the divergence theorem. The book, or the proof is not terribly difficult, and the textbook provides a nice sketch of that for a simple solid region. We'd rather spend our time working with this theorem and extending it to at least one physical example. So we'll do that instead. We'll let E be a simple solid region that's bounded by the surface S with positive outward orientation. Let F be a vector field with components that have continuous first partial derivatives on an open region R3 containing E. Everything that we would expect to be the case. We've always assumed continuous first partials in any of these theorems. So nothing new here. And really any problem we see, we'll have all these things taken care of. Now, the double integral of F, the vector field along this surface, is equal to the triple integral of the divergence of F over the solid region E. So remember that S is the boundary, this 2-dimensional object. E is the solid region, which is a 3-dimensional region. That's the contents, essentially, that S is the skin that's wrapped around it. Okay, so we really can interpret the divergence theorem as the flux of the vector field F through the boundary surface or across the boundary surface of E is equal to the triple integral of the divergence of F over E. So let's use it directly in an example just to get familiar with it. Much like any of the other vector calculus theorems we've worked with already, we've got one way or the other we might be able to evaluate a problem. So that's the left here or the right, a double integral or a triple integral, just depending on which is easier. They ask us in the first example to find the flux of the vector field F over the unit, or F given as we have here, over the unit sphere given here. So we've got two choices. We could use the surface integral of F dotted with the normal, or we could use the divergence theorem to calculate that same quantity. Now, just to exercise the divergence theorem, we will make this step and evaluate the triple integral. It would be very useful for the student to go back and verify or confirm Stokes' theorem, or sorry, the divergence theorem, or verify the divergence theorem by calculating the left-hand side. In other words, calculating the surface integral of this vector field over the unit sphere. But that could be a hard problem. In this case, I don't think it is. But what you'll find is you should get the same answer that we got here for this triple integral. Now, the actual calculation of this is fairly straightforward. We just recall that the divergence of F is partial of x with respect to this component, partial of y with respect to this component, plus the partial of z with respect to this component. That left us with 0 plus 1 plus 0. Remember that divergence of F is really the del operator dotted with F, so that we have a sum of objects on the right. And that's exactly what's happened here. Our divergence comes out to be 1, and that is our integral term. But then we would quickly realize that, well, even if this is 1, which is simple, we are integrating through a spherical region in R3. That's what E is going to be. So spherical coordinates will be the easiest way to conduct this or perform this integral. So rho should range from 0 to 1. Our radius should range from 0 to 1. Phi, the z-axis angle, should go from the positive z-axis at angle 0 down to the negative z-axis at angle pi. And then theta should sweep throughout the entire xy plane from 0 to 2 pi, and that will form our sphere. So here's our divergence. This is the spherical integral formula component, rho squared sine of phi, and then d phi d, or d rho d phi d theta. And this is a straightforward integral. First is an antiderivative power rule, limits of integration applied. Next is antiderivative of sine phi, given here, evaluate from 0 to pi. And lastly, the antiderivative of, well, a constant times d theta, and we get theta from 0 to 2 pi. The answer is 4 pi over 3. Fairly straightforward integral. I'd be surprised if finding the flux over this surface directly was, in other words, evaluating this integral. If that was any easier, that would be surprising. But I do think it's doable, and it's worth the exercise for the student to take care of. Again, you should arrive at the same answer. Let's use it again. A little bit more complicated surface or solid that we're dealing with. We're asked to calculate the surface integral, or that is the flux of F across S for this vector field. So already slightly more complicated than the vector field we saw previously. And of course, the solid itself is a little bit more complicated. It's not simply a sphere anymore. It's the cylinder with upper border or upper surface bound z equals x plus 2 and lower surface bound z equals 0. So z equals 0 is just a disk in the xy plane. That's down here. Now, what's going on up top on the cap of this cylindrical region is it's angled downward. So it starts here and it cuts downward into the page away from us as we look at it. It's sort of hard to draw that. I did dot the back end of this so it looked that way, but it's we'd imagine if we rotated the axes 90 degrees, we should see something that looked like this, more or less, just to kind of give you an idea of what this thing looks like. A cylinder that's been cut at an angle, and we'd have to rotate this back 90 degrees to put this this low side back into the page. Regardless, we can pretty easily handle this situation just because of our practice with triple integrals already. We know that z is going to range between 0 at the lowest up to x plus 2 at the greatest. So that'll be a limit of integration for that variable pretty much right away. So first things first, and probably the best way to start any one of these problems, if we're looking for the flux of a vector field across a surface S in three dimensions like this, we might just consider the divergence theorem right off the bat. And the best way to consider whether or not it's useful is to just have a look at what the divergence of F is. Take del dotted with the function or the vector field F. If we get something reasonable, workable out of it, then maybe it's going to be a good integral. This one's questionable from the start, but we do notice there's one factorization we can make. 4x can factor away from both of these components. We realize 4x times x squared plus y squared is actually what we've got here. And we know that we're dealing with a cylinder, partially a cylinder. So we might end up using cylindrical coordinates, or at least polar coordinates, which is essentially kind of one and the same before we're done. So this would actually be r squared. This would be r cosine theta. This might work out favorably as an integrand. So you don't know until you really get further into it, but this is a decent hint that this one's going to go okay. So in other words, we wouldn't just directly attack the flux integral of F through the surface S. One reason we might not want to do that is this surface, this object, is somewhat complicated. We've got a surface up here that we'd have to write down. We've got a cylindrical surface on the sides that we'd have to integrate for, and we've got a circular surface at the bottom of this cylinder that we'd have to account for. This, of course, the top is an elliptical surface. So that's at least 3 different integrals that we'd have to handle for these different surfaces for the flux of F through S. We'd have to break this thing down into the union of those 3 surfaces and sum up those 3 double integrals. That might not be something we want to do. So the divergence theorem lets us jump into this triple integral over the solid region E enclosed by these surfaces, and that's of the divergence of F. So integrating from 0 to x plus 2 with respect to z, and I've left this sort of packed. We haven't broken that into a coordinate system yet. Maybe we'd stick with dx, dy in rectangular coordinates. Maybe we'll switch to cylindrical. We have a good feeling we're going to switch to cylindrical just because, after integrating z from 0 to x plus 2, which is essentially here up to this plane, all that's left is the cylindrical region D at the bottom of this circular disk that we need to integrate through. So we will, in fact, convert to polar, but we've left our options open just in case we saw some other opportunity. So integrating this expression with respect to z, well, there is no z in it, so that's all constant with respect to z. So we just end up with z as the antiderivative of the constant, and then evaluate it from 0 to x plus 2. Well, at 0, that's 0. And then that z at x plus 2 just adds a constant of x plus 2. So here's our z. The other one was minus 0 times all of this, and that didn't show up in this next line then. So progressing from here, it has gotten a little bit messier, but we'll note that this is 4x squared plus 8x here. So we can then express D as this circular region. That won't be too bad. Given that this part here is actually going to be r squared, things will simplify nicely. So D is the circular disk from 0 to 1, for r, and theta ranges from 0 to 2 pi. Remember the substitutions: x is r cosine theta, y is r sine theta. And we have mostly x's in this. And we have 4x squared is now 4r squared cosine squared theta. And then 8x is 8r cosine theta. And then this term became r squared, as we said it would. Now this is r from our polar coordinate integration formula, or change of coordinates, dr d theta, to finish off the differentials. Ultimately, we end up with r to the 5th here, and an r to the 4th here. Those details are kind of suppressed, but fairly straightforward to fill in the intermediate step. The antiderivative with evaluations at the endpoints 0 and 1 look like this. Dividing by our constants from the power rules. And we have a fairly clean trigonometric integral next from 0 to 2 pi in both cases, cosine squared theta d theta. By now we've done so many of these. This is calc 1 off to the right, cosine theta. And applying the limits of integration after finding these antiderivatives, or just recalling them, we end up with 2 pi over 3 in the very end. So that is a more complicated problem. I think we can see the utility now in this case of the divergence theorem, namely in not having to break apart this region into at least 3 different surfaces, possibly more. We just have one triple integral, and it's not too bad. We just have to make some conversions to polar coordinates to handle it. Or maybe technically we can think about it as being in cylindrical coordinates, because after all, that was a dz to start with. Okay. So extending this theorem a little bit further, remember that we did the same for Green's theorem. If we had simple closed curves, we were able to extend it to unions of simple closed curves. In this case, we'll do the same for simple solid regions. If we have a union of simple solid regions that comprises E, some solid E. So I've drawn one such of these, similar to what the textbook has. The picture in the textbook is certainly better than what I've got here. But this red portion in here is the boundary of some smaller solid. It's actually a cavity inside a solid region, E, of this other elliptical outer region. So the content of this, whatever the material might be, if this was a material, is actually in this region, whereas in the red region in here, this is open, this is air or vacuum, or no matter is in there, no material is in that. So this is this solid E has 2 boundaries, 2 surface boundaries. S1, its inner boundary, which bounds the solid material out here from the air inside there, or vacuum inside there, and then this outer region here, the obvious one that we've dealt with in the past. Now the issue is the outward pointing normal for this surface is exactly what we want for E. It is an outward pointing normal for the solid E. However, for this surface S1 that makes up the inner boundary, its outward pointing normal points into the material or into the solid. That's opposite from what we actually want. From how we defined it, we want it to point away from the solid, so we have to take it as negative in 1. And that's what we'll do above, and this is why we have the normal declared as is in the text here. And so essentially all of this has been explained in the picture, the text that we see here. Namely, we'll take the normal to be negative in 1 on this surface S1, and to be positive in 2 on the surface S2, which is the outer bound. So the divergence theorem tells us this equality, that the triple integral of the divergence of f of this surface E is equal to f dotted with the normal vector along its surface boundaries. Now that, of course, S is the union of S1 and S2, because there are 2 different boundaries for this solid region E. So we split up that union of boundaries as the double integral over S1 and the double integral over S2. Of course, N is now negative n1 for S1, so we have the correct orientation and the positive orientation of our normal vector from our solid. N is positive n2 here. And we can just factor this minus sign out, rewrite this integral as f dot ds and f dot ds for each of these S1 and S2 surfaces. The only difference now is there's a minus sign right here. So we'll use this result below, and there may be an example or two in the exercises where this would be a useful thing as well. I believe certainly in the homework on WebAssign that will be the case. Now, ask us to consider the electric field. I think we've always had this as an optional example since we started looking at vector fields in this chapter. But we consider the electric field given by E of x. X is a three-dimensional vector, so an R3. Two constants, epsilon and q. Q is the electric charge. Epsilon's a constant. X is our, of course, vector position in the plane, and this is our magnitude of that vector cubed. So that is our electric field as given, not uncommon. And let's see, they ask us to use the divergence theorem to show that the electric flux of E through any closed surface that encloses the origin is given by this quantity right here. So this is a nice broad result. It would be nice to be able to have that. So again, to restate that, the electric flux of E through any surface S that encloses the origin is given by that constant. So that's any closed surface S with the origin inside of it. Okay, now that's going to be difficult on the surface, no pun intended, because you know, that could be any arbitrary surface enclosing the origin. So what we'll actually use is one surface up here that is that arbitrary surface, and the other one will be some nice sphere either completely inside that surface or completely outside of that surface. It doesn't really matter which one we choose as long as we can fit it one way or the other. We'll choose, we'll just choose a sphere of radius A, and we can suppose that it's small enough to fit inside and around the origin, and we'll go from there. So S sub A will be a sphere of radius A, chosen small enough to fit inside of our original surface S. And first thing that we should note, this is the most useful part of this problem, is that the gradient, sorry, the divergence of the vector field F is the divergence of this expression. And note that epsilon and q are constants, so they'll factor to the front of this dot product. Now, x is the vector x, y, z, and we're taking the gradient of that with we're taking the divergence of this vector x, y, z. Each of these components is divided by the magnitude of the vector cubed, and that's what we see below. So the reader is encouraged to carry out the details of this. It'll be partial of x times this component and this, or over that, plus partial of y times this component over this, plus partial of z times of this component over this. And those will be all three quotient rule partial derivatives to take. Be careful with the details, but you'll find that when you do simplify it, that divergence, that calculation does in fact come out to 0. And that's key, because that means that we can use this result above, up here, that the divergent, the integrand of that triple integral is 0, which means that overall that left-hand side is 0, which then means that these two integrals on the right-hand side are equal to each other. So what that tells us in our problem is that if we fit a little sphere inside of the surface S1, thanks to just the nature of this vector field, we'll be able to say that the flux through this surface, this flux integral is equal to this flux integral for that tiny little sphere that we fit inside the larger surface enclosing the origin. So that means we don't have to calculate it on any general surface or any arbitrary surface. It'll just match whatever the sphere's surface integral is or flux integral is. So And that's what we've got written here, that, that this surface integral for the general region is equal to the surface integral over the sphere plus the divergence. So really what we've done from above is we've added this integral over to the divergence side, or vice versa, but the minus signs will all line up and work out no matter which way we decided to do that. And so we're left with this surface integral on the sphere with radius a centered at the origin. Okay, now we know that the normal vector in this case for this surface integral is, what's the normal vector of a sphere, which is just for any sphere centered at the origin, this expression here, the vector x divided by its magnitude. Just take a minute to think about that, make sure it's true. Now, this means that we've got this vector x dotted with x over the magnitude of x. So we end up with the magnitude of x times the magnitude of x cubed is magnitude of x to the fourth, and then x dotted with x here, remember that is a vector dot product. These parts were scalars, so they just multiplied as a scalar would, but x dot x is a vector operation. And remember that the dot product of a vector with itself, in other words, x dot x, is equal to the magnitude squared. So this will be, on the next page, the magnitude squared because of this identity right here. We'll recall that x dotted with x is magnitude squared. One last little bit. Epsilon and q are constants with respect to any of these variables, so they just factor to the front of the integral, simplifying our integrand as we have it. So on the next page, we end up with this slightly more straightforward looking integral. 1 over the magnitude of x squared over this spherical surface S sub a. Now, another point we need to remember is that the equation of this sphere is literally the magnitude of x is equal to a. It's a sphere centered at the origin with radius a. So that completely makes up what we'd expect. And so we can substitute 1 over magnitude of x squared with 1 over a squared. So this is a constant with respect to this integral. And that also factors to outside of the integrand. And we end up with just the integral over this surface, S sub a. So really this is just the area of the sphere of radius a. And if we go back a couple sections to the parametric surfaces that we dealt with in the past, we found that the area of a circle, of a spherical surface of radius a is given by 4 pi a squared. That calculation is worth doing again if the reader just doesn't remember it at all, but this is noted right here. And when the a squareds cancel out, we're left with exactly what we're asked to prove, 4 pi epsilon q. So that is our electric flux through any surface that contains the origin. Now lastly, we'll use the divergence theorem just to interpret what the divergence of a vector field actually is, much as what we did for Stokes theorem, for the curl with Stokes theorem. So we'll consider a fluid flow that has velocity field v of x, y, z. Rho will be the constant density of the fluid. So our flow rate per unit area is F equals rho times velocity. Now let P naught be a point in the fluid and B sub A be a ball with some small radius A around P naught, centered at P naught. Since F is a continuous, since the divergence of F is continuous, we can use this approximation, and A is fairly small, so the points P that are in the ball B sub A are pretty close to P naught, so the divergences are fairly close in value. Now, of course, the smaller A gets, the better this approximation actually is, the more accurate it is. We'll get to that in a moment. Now that the approximate flux of it over the sphere's boundary then is given by this integral here. The divergence theorem tells us that's equal to the triple integral over the entire ball of the divergence of f. Now looking at the divergence of f for any point in this ball, we have that it's approximately equal to the divergence of f at p naught, the center of the ball, which is a constant. So we substitute that in, and this approximation matches that more or less, or implies that. And what we realize from here is that the divergence of f at p naught, this is a constant, just like we saw in the previous example. So it factors out, and we're just looking at the volume of this ball, b sub a. So we'll just write that down as is, the volume of the ball, b sub a off to the right here. So our flux over the sphere's boundary is approximately equal to the divergence of f at p naught times the volume of the ball. Now let's rearrange this a little bit to get the divergence by itself, and this is what we have here. And we'll let a go to 0 to make this approximation exactly equal. And what we arrive at is this limit equation right here. The divergence of f at this point p naught is equal to the limit as a goes to 0 of 1 over the volume of b sub a of the flux integral of the divergence of f across s sub a. In fact, this is this divergence actually should not be here. That's a typo. So interpreting this, as we have it in front of us, we see that the divergence of f at p naught is the net rate of outward, right? F dot ds is f dotted with the normal, which is the outward pointing normal on this surface. So it's the outward, the net rate of outward flux per unit volume at a point p naught. Okay, so it's some measurement of something, fluid flow coming into or fluid flow leaving the point p naught. And that's exactly what we suggested the divergence was in 2 dimensions, and we're just seeing it now in 3 dimensions. So with that in mind, if the divergence of f at p naught is greater than 0, then the net flow overall is outward. We're pushing more material outward than we're taking it in, whatever this flow might be. And we're still talking about a fluid flow here, but it could be an electromagnetic flux or something like that. If this is the case, then if the flow is net outward, then we call it the point p naught a source. It's creating, or it's a source of some fluid flow or whatever the flux might be. If the divergence at this point is negative, then the net flow is inward at p naught, and we call that a point of sink in that case. So below, we've got some drawings of this. This is the ball BA with its surface boundary S sub A. The ball was centered at the point P naught that we used above for this derivation. But sources and sinks might look like this. Notice the vectors coming into this point P naught are smaller than those leaving the point P naught. So this would be a source. There's more leaving P naught than there is coming into it. Now, this is just a sketch. And it's, we don't see every vector that comes in here, so there are more questions about how that is, cumulatively. But this is just to suggest what a simple version of it. Now, a sink might look like this. The vectors coming into P naught are smaller than those leaving it. Another type of source or sink that we might see in some vector fields might look completely like this. A source might be emitting flow or flux at all points. Right, so that's another version of a source. And a sink might do the opposite. All the arrows might point at that point as well. But just note that they don't all have to point in or away from a source or a sink. It just has to be the net effect, as we see in these two cases here. So that's an interpretation of the divergence in 3 dimensions, thanks to the divergence theorem. And that essentially completes everything in this section and the chapter and the course. So keep in mind that there are a few problems in the exercises where this equality will be useful. I think 2 or 3 problems are like that. So you'll have to calculate one of these flux integrals to come up with the flux integral of the other one, and you'll possibly have to come up with, and you'll have to calculate this triple integral as well. This is the only type of example we haven't seen, but it can be readily handled through this identity.